Hey everybody, so we've got a couple more derivative things to do here. So let's just start with this function f of x equals x cubed, and let's compute its derivative. It's always good to remind ourselves the definition. The derivative here is the limit as h goes to 0, f of x plus h minus f of x all over h. And so we can take, it'll be x plus h cubed minus x cubed over h. So what is this? X cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. These x cubes will cancel. We can pull a factor of h out of everything in the numerator. So we'll have h 3x squared plus 3x h plus h squared over h. Those factors of h cancel, and we are left with a simple polynomial. 3x squared plus 3x h plus h squared, right? A polynomial in h. We're thinking of h as the variable here for the limit. And we can just plug in 0 for h since it's a polynomial. So those last two terms disappear and we get 3x squared. So here we have f prime of x is equal to 3x squared. Okay. So what does this function do, right? So this is our idea that the derivative can be thought of as a function. What does this derivative do? The derivative spits out the slopes of tangent lines, right? So if we wanted the tangent line to f of x at x equals 1, well, what do we need? We need a point. So the point will be 1 f of 1, which is of course just 1, 1. And we need the slope. The slope is going to be given by this function, f prime of 1, which is 3 times 1 squared, or just 3. And so with this function in hand, we can compute the derivative, the tangent line. So y minus 1 equals 3x minus 1 gives us an equation for the tangent line. Let's take a quick look at this. Here is that graph. And here's that tangent line. Oops, there we go, at 1, 1, right? Great, this is exactly what we built the derivative for, and so this is fantastic that we can do this. However, let's go back and look at this derivative, right? We're saying this new formulation, we started with the derivative at a point, but then we decided to make the derivative a function. It's a function, just like f was a function, f prime is a function. Functions have derivatives. They don't always, we've seen that there's points where they don't, but in general, a lot of the functions we deal with will. And so it's reasonable to say, can we take the derivative of this derivative? We have a definition, we can apply that definition. So let's try this. The symbol we use, we're taking the derivative of the derivative. We're just going to take f prime prime or f double prime. The definition is the same. The limit as h goes to 0, f, except now the function isn't f, right? When we find the derivative, we look to the original function. We're finding the derivative of the derivative. So instead of f of x plus h, we're doing f prime of x plus h minus f prime of x all over h. The limit as h goes to 0, so we'll have 3x plus h squared minus 3x squared all over h. Limit as h goes to 0, so we'll have 3x squared plus 6xh plus h squared minus 3x squared all over h. We can factor out the 3x squareds cancel. And then we can factor out an h, so 6x plus h over h. The h factors cancel, and we get a limit as h goes to 0 of 6x plus h equals 6x. And so what we have here, f double prime is equal to 6x. So just like f prime tells us slopes of tangent lines to f of x, f double prime tells us slopes of tangent, missed an S in there, tangent lines to f prime of x, right? So this function f prime of x 3x squared, we know what that is. That's a parabola. It's going to have tangent lines too. If we wanted the tangent line to f prime of x at x equals 1, we do the same process. We have the point 1 f prime of 1, which is going to be 1, putting in 1 for x squared, we get 3 times 1 squared, or 3. And then the slope will be f double prime at 1, or 6. And so the equation of the tangent line will be y minus 3 equals 6, x minus 1. Let's look at this graph. So here's y equals 3x squared, right? We found it because we were looking for the derivative of f of x. But if I had just given it to you, the function y equals 3x squared, and said find a derivative, that wouldn't be surprising. It only might seem strange because we thought of it as the derivative of something else, but then we're taking it as a function in itself and taking a derivative of it. And so we call it the second derivative of f double prime. We found the tangent line. There was the tangent line to this derivative at x equals 1. We could keep going with this. The second derivative, we can take a derivative of this function. Or sorry, we did take a derivative of this function to get this line, y equals 6x. That's a function. I could take a derivative of that, which will turn out to be 6 in this case. But there's no reason we have to stop at any point. The derivative produces a function, right? The derivative of a point produces a value, but the derivative function is a function, and we can take derivatives of functions, or at least we can attempt to, right? You'll find cases in places where derivatives aren't possible, but in general, this is something we do to functions, and so if it produces a function, we can do it again. Okay, let's mention some notation, right? So we've already seen that if we start with a function f of x, we can take the derivative. Remember this notation, d dx of f of x will give us f prime of x. Then we could take the derivative of f prime of x and get f double prime of x. You could continue this. We could do f triple prime. Usually after this one, people start using little parentheses because it would get ridiculous to keep putting all these little hash marks there. But the first 2 or 3, people usually put the little hash marks. And there's no end to how far we can go, right? In general, right? There's some functions that might run out of derivatives or become undifferentiable at certain points and things like that. But in general, there's no reason we have to stop taking derivatives. Another set of notation, right? We talked about the derivative. Another way to write that was dy dx, right? Well, when we take the derivative, so this is a function, so I could take the derivative of this function. And the way we write this is a little bit strange. D squared y dx squared. right? So it's sort of like, it's just a weird notation. You just have to live with it. You can kind of think there's a D on top, so there's a D there, so we've got two of them. They're not being multiplied in any sense. It's just a notation that we use to do that. And then if you want to take a third derivative, we get D cubed y dx cubed, and so on, right? You can keep going with that one as well. Okay. So the important thing, at least for computing them, is to remember nothing changes about the rule. You just have to remember, if I'm taking the second derivative, the first derivative is the function, right? I start with, when I take the first derivative, I've got f of x plus h minus f of x over h. When I take the second derivative, it's f prime of x plus h minus f prime of x. If I take the third derivative, it's going to be f double prime of x plus h minus f double prime of x in that numerator, right? So whatever function you're taking the derivative of, even if it happens to be a derivative, is the thing that goes in there. Let's end with giving this a little bit of meaning, okay? So in general, when we have a function, y equals f of x, and we take the derivative, y prime equals f prime of x, it tells us, this is a function that tells us the slopes of the tangent lines, right? Slopes of the tangent lines, right? Well, we can think of that as the rate of change of y. Well, let's write this a little different. Well, with respect to x, right? And so when it's not mathematical, so we can say this as change in y over change in x. When it's just mathematical, when we don't have units or an idea, that can be a little bit abstract, but it just tells us, how does the output variable change as the input variable changes? Second derivatives do a very similar thing. So if I do y double prime equals f double prime of x, it's how does the change of y, how is that function changing as we change x, right? This is a little bit abstract. Let's think of it with some meaning that hopefully makes it clearer. If I have the function x of t, which gives me position at time t. Let's give this units. So the position, let's say it's spitting out meters, and the input is going to be seconds. Time is in seconds, right? When we take the derivative, this is how does position change in position as we change time, right? And the units are meters over seconds, right? Or meters per second. So how your position changes as time changes is a measure of velocity, right? I'm moving that way 4 meters per second. That means if a second goes by, I'll be 4 meters, my position will change by 4 meters. I'll be 4 meters in that direction. The next second, 4 more meters. We call this velocity, v of t, right? Well, x double prime of t means taking the derivative of x prime. That means, well, what is x prime spitting out? It's spitting out velocity. So this is telling us, how does our velocity change in velocity? What were the units of velocity? Meters per second. As we change time, right? We're still changing that same input variable time, which is per second, right? So this might be something like, so what we want to say when you look at this is, let's say this turns out to be a 5 meters per second per second. What that's telling you is how much the velocity is changing. If I'm going 10 meters per second and the change in velocity every second is 5 meters per second, then if I start at 10 meters per second and 1 second passes, I'm now going 15 meters per second. And then if another second passes, I'm going 20 meters per second. I'm speeding up, right? So it tells you how much velocity you're gaining every second, okay? So the units here are meters per second per second. What people typically say is meters per second squared, because you've got a per second, right? But it kind of hides what's actually happening. It's how does the meters per second change every second? We have a name for this: acceleration. Okay, so these higher order, there's names for the other ones. I can't remember off the top of my head what the next one is. The pulse or something. The jerk. I think the jerk is next. Like how quickly it jerks to a start. Is how I think about it. But anyhow, this is a really good way to think about this: position, velocity, acceleration. Right? Position is in meters. Velocity, we get meters per second. And acceleration is meters per second, which most people write meters per second squared, okay? But what it really means is how does the meters per second change every second? Just like velocity was, how do the meters change every second? Okay, those are the higher order derivatives, is what we call those. And that's it for this one. Thanks, everybody. I will see you next time.